Hello students and welcome to the 55th lecture on particle physics. And in the last turn we were discussing about writing the wave function, the baryon wave function using quarks, and we found that in general when we write the baryon wave function, it consists of the wave function for the spatial part, then the wave function for the flavor part, wave function for the spin part and the color part, while the total wave function should be properly normalized. Now we have evaluated in the last lecture the charge of delta plus plus, and we found that for this we have to evaluate the using the charge operator taking between the wave function of the delta plus plus. Since we saw that the spatial part, spin part and the color part, they have nothing to do with the charge operator. It should be only the flavor part. Therefore, we considered u in state 1, u in state 2 and u in state 3. Then initially we took all the three operators E1, E2, E3 to operate on particle in state 1, particle in state 2 and particle in state 3. Then later we realized that instead of doing it individually, equivalently what we can do, we can take E3 only and apply it on the particle which is in the third state, and that is why here I have written it as 2 by 3 E times 3, because this 2 by 3 is we are getting when the E3 operator is operating on U particle in state 3, and this is giving me 2 times the electronic charge. Similarly, if I talk about evaluating charge of delta minus, then this will be 3 times D1, D2, D3, the E3 operator operating on D1, D2 and D3. Now E3 will only operate on D3 and this will give us minus 1 by 3, and therefore this will be 3 times minus 1 by 3, and then we have D1, D2, D3, D1, D2, D3, and these are normalized. Therefore, we are getting it to be minus 1. This is how we calculate the charge of a particle. Then we come to the spin part. We know that there are 3 spin operators. Like we are talking about, instead of E1, E2, E3, just we have to talk about E3. Here also we are only talking about sigma 3. If you recall, the sigma 3 matrix is represented by 1, 0, 0, minus 1, and spin up state is represented by a column matrix 1, 0. Therefore, this is giving us 1, 0, and 1, 0 is nothing but the particle in spin up state. While sigma 3, when it operates on spin down state, it gives us minus 1. That means eigenvalue, if sigma 3 operates on spin up state, it is plus 1, and when sigma 3 operates on a spin down state, the eigenvalue is minus 1. Now let us talk about the different states that those we can discuss in this class. Like if I am talking about the mixed symmetric states, like this is 1 by root 6, up, down, up, minus down, up, up, or plus down, up, up, minus twice, up, up, down. Or we talk about the antisymmetric part for spin half object, 1 by root 2, up, down, up, minus down, up, up. Okay. Therefore, these are the 2 possibilities. Now, sigma 3 will operate here. These are all orthogonal states. Therefore, we can calculate what will be this value. For example, if I say that What will be the value for MA? Sigma 3 MA here. This will be 1 by root 2, 1 by root 2 from both the sides, 1 by 2, and then up, down, up, minus down, up, up, and then sigma 3 operator, up, down, up, minus down, up, up, and this will be sigma 3 operating on this will give me a plus 1 eigenvalue. Sigma 3 here also will give me plus 1 eigenvalue. Therefore, this will be up, down, up, minus down, up, up. As you can see, this will be up, down, up, minus down, up, up. And then this state will give me value 1. This with this orthogonal state will be 0. This with this orthogonal state will be 0. This with this minus and minus sign will become plus. And what we will have? What we will have is 1 plus 1 divided by 2, and that is nothing but 1. This is what I have written it here. Therefore, if you have such type of states, then it is 1. If you have, and then this is 0 because these are orthogonal states. And then we have, for example, if we take this case, psi ms, sigma 3, psi ms, then in that case this will be minus 1 by root 6, up, up, plus down, up, minus twice up, down. Sigma 3 operating on 1 by root 6 with a minus sign, up, plus down, up, minus twice up, down. And you see, sigma 3 will operate here, will give me plus 1 eigenvalue. This will give me plus 1 eigenvalue. But up, down, when it will operate on a down state, it will give me minus 1. Therefore, if you notice, this will give us minus 1 by root 6, minus 1 by root 6 will, when we will take them out, this will be 1 by 6. And then we have up, plus down, up, minus twice up, down. And here we are getting up, plus down, up, minus plus twice time up, down. And this will be 1 by 6, 1 plus 1 minus 4, 2 2s are 4, and this minus sign is there, and that is minus 2 by 6, and that is minus 1 by 3. And this is what minus 1 by 3 we are talking about. Therefore, if we are talking about spin half objects where we have two possibilities, mixed symmetric and mixed antisymmetric wave function, we can evaluate the expectation value corresponding to the spin operator. Similarly, we can calculate the expectation value corresponding to the charge operator. Now, the magnetic moment operator is defined as mu n ei sigma I z. And we know that mu p by mu n, when we will calculate it in the quark model, this will turn out to be minus 3 by 2. That will be minus 1.5. While when we will go to the experiments, experimentally this is turned out to be mu p by mu n is 2.79 nuclear magneton for the proton and minus 1.91 for the neutron, and this is minus 1.46. You can see that the magnetic moment of the ratio of the magnetic moment for the proton to neutron using the quark model turns out to be very close to the magnetic moment of the experimentally measured value. And that is why we believe in the quark model, that the quark model gives us the correct result. And this is what we have discussed just now for the particle which has got a spin half, whose projection is plus half. This is the result. Similarly, for the mixed symmetric case, we have obtained this as minus 1 by 3. And for mixed anti-symmetric case, we have obtained it to be 1. And if we consider, see here there is an important catch. The Wheeler wave function for the proton and neutrons or deltas, they will be different. But when we are talking about proton and neutron and want to evaluate or want to study simultaneously the properties of proton and neutron, then there is no reason to take the proton spin to be in spin up state and the neutron spin to be in spin down state or vice versa. If we are, because what I have told you in the last class, that if we have got 100 of protons or 100 of neutrons, and if they are not polarized, then 50 of them will be in spin up state and 50 of them will be spin down state. Therefore, if we are evaluating the property of proton and neutron, then flavor wave function will be different for the proton and neutron, that we have seen. But the spin wave function, if we are taking the spin projection to be plus half for proton, then we have to take plus half for the neutron. Or if we want to stick with minus half for the neutron, then the spin projection will be minus half for the proton also. But here for the completeness, what I have done, I have also taken evaluated the expectation value when we have the mixed anti-symmetric wave function. And as you can see, this is the down, instead of up here, we have a down spin. And this, when you will evaluate it, this will turn out to be minus 1. While when we talk about the charge operator, you see the charge operator for the proton case, for example, for the mixed symmetric wave function, I am talking about the proton. For the proton case, see 3 factor is again, this factor of 3 is coming because we don't want to evaluate it for particle in state 1, particle in state 2 and particle in state 3 independently. Instead of that, we are saying that equivalent result we will get if E3 will operate on the particle which is in state 3. Therefore, this will be minus 1 by root 6 u du plus duu minus twice uud 3 minus 1 by root 6 udu plus duu minus twice uud. And you see E3 will operate on u. This will give me 2 by 3 times the electronic charge and will return back this state. E3 will operate on u. This will give me 2 by 3 the electronic charge, return back this state. E3 on operating on the d quark will give me a minus 1 by 3, and that minus 1 by 3 will make this plus 2 by 3. And therefore, if you notice, I can write this as minus 1 by root 6 minus 1 by root 6 outside. That will give us minus plus 1 by 6 and 3 outside. That means this is 1 by 2. Then what I have? U du plus duu minus twice uud, and then u du plus duu plus 2 uud. And these are orthogonal states. Therefore, this with this will give us 1. This will give us 1, and this will give us minus 4. Therefore, the number that you are going to get here, 1 plus 1 minus 4, and that will be simply minus 1. This will be for the mixed symmetric wave function for the proton. If I talk about the mixed anti-symmetric wave function for the proton, then recall this will be Ma ma, and here this will get changed to, because mixed antisymmetric wave function will be 1 by root 2 u du minus duu 3 1 by root 2 u du minus du. And then you see E3 will operate here, will give us 2 by 3 electronic charge. Here also it will give me 2 by 3 electronic charge. There will be no change of sign. Therefore, this will be 3 by 2 and then 2 by 3 electronic charge from here, and minus plus 2 by 3 electronic charge from here. And this will give us how much? You see 4 by 3 electronic charge, and this 3 and 3 will cancel out. Here it will give 2e, just its number will be 2e. Here also I should write it minus 1e. Therefore, this is how then we will put it in the terms to get the charge of the proton. That we will do in the class. And therefore, you see that when we want to evaluate the magnetic moment of the proton, we have both the charge operator and the spin operator. Now, when we have the charge operator, it will operate on flavor wave function. When we have the spin operator, this will operate on the spin wave function. And since we have the space part which is independent of these two, we have taken them out. Color part, we have taken them out. But at the same time, we have then a mixture of spin part and the flavor part. And what I had told you when I wrote psi b as psi r times psi spin, psi iso spin and psi color, that this has to be antisymmetric for baryons. This by construction is antisymmetric. This is always symmetric. Therefore, this guy has to be symmetric. While when we evaluated the flavor wave function for proton and neutron, we found out that we are getting mixed symmetric as well as mixed antisymmetric combination. Now, the important point is mixed symmetric times mixed symmetric will give me a symmetric combination, and mixed antisymmetric times mixed antisymmetric will give me a symmetric combination. While mixed symmetric time mixed antisymmetric will not be allowed, because this will give me antisymmetry, and antisymmetry with antisymmetry will become symmetric. That is not allowed. Therefore, we are taking a normalization factor when we are putting these two together. This is F. We are writing for the flavor part, that means the isotopic spin part, and this we are talking about the spin part. Therefore, we have 1 by root 2 times this psi mixed symmetric flavor, psi mixed symmetric spin, plus psi mixed antisymmetric flavor times psi mixed antisymmetric spin, and then this is the operator. And then what is the important catch? Then again here we have 3E3 sigma 3Z. 3 we will take out. E3 will operate on the flavor wave function. Sigma 3 will operate on the spin wave function. Either I write sigma 3 or I write the Z, that is one and the same. When you will evaluate this, you will obtain a value which will be just, because the magnetic moment is measured in units of nuclear magneton, this value will be just mu n. While when you will do it for neutron, this value will turn out to be minus 2 by 3 mu n, such that the ratio of neutron to proton is minus 2 by 3. This is what we get in the quark model, the magnetic moment ratio for the neutron to proton. Therefore, here it comes with the, for the magnetic moment, it comes with the inner charge operator as well as the spin operator, the way we have described the magnetic moment. While for the charge of the proton, charge of the neutron, etc., you need only the flavor wave function. You can take it as a homework that how to obtain the charge of the proton, neutron and other particles using the flavor wave function in SU2 model. Now, the other important point, it was proposed that the difference in the masses of K plus and K plus star or pi plus and rho plus is due to the relative orientation of quark spins, and that is due to the different spin-spin interactions. Therefore, if we want to talk about the mass of the baryons and mesons using quark model, we have to keep in mind, if you can recall, this was K plus, K0, K0 bar, K minus, pi plus, pi 0, eta 0, eta 0 prime and pi minus. This was rho plus, rho minus, rho 0, omega 0, phi 0, K plus star, K0 star, K0 bar star, K minus star. You see, this is particle with spin 0 parity odd. This is the particle with spin 1 parity odd. Quark combination for both of them are the same, but the masses of K plus and K plus star are different. Mass of pi plus and rho plus, they are different. Mass of pi 0 and rho 0, they are different. Quark composition is the same, but why there is a difference in masses? Therefore, to understand that, for similarly, this you can talk about a proton and a delta. This mass is 938, this mass is 1232. Similarly, mass of sigma plus and sigma plus star. This is a spin half particle with positive parity. This is a spin 3/2 particle with positive parity. The masses are different. Therefore, in the case of baryons as well as mesons, what we find out that though the core combination for them, both the particles are the same, but masses are different. To understand that, what was proposed, that it is actually happening because this is a spin half object and this is a spin 3 half object. Therefore, when quarks are combining to give a total spin half object, or quarks are combining to give a total spin 3 half objects, the combination is such that one is resulting in a lesser mass than in comparison to the particle which has got a spin 3/2. Similarly, for the mesons, one that has spin 1 has a greater mass than spin 0 particle. And that means it is basically because of the spin-spin interaction between the two quarks. And that is what we are talking about. That if we talk about mesons, then we know that mesons are made up of quark-anti-quark pair. Therefore, the mass of the meson will be the mass of quark plus mass of the anti-quark plus an additional term we are writing that is proportional to the quark spin-spin interaction, like we have the hyperfine structure in the hydrogen atom or in general in the case of atoms. Here we are talking about the spin-spin interaction, and we are saying that mass of the meson is mq plus mq bar plus a sq dot sq bar upon mq times mq bar. They will be written in such a fashion that all these three terms will be in MEV. That means this A, which is a proportionality constant, when we will determine it, it will be written in such a way that the total dimension of this will turn out to be in MEV. Therefore, what we are saying that if we have two objects, S1 whose spins are S1 and S2, then the expectation value of S1 dot S2, because this is the real value, real numbers that we will get when we will talk about the spin interaction. This is what is written here, SQ dot SQ bar. This will be, expectation will be the multiplicities of a state S square will give me S times S1, S plus 1. S1 square will give me S1 times S1 plus 1, and S2 square will give me S2 times S2 plus 1 divided by 2. That means what I have done, I have written S square as S1 square plus S2 square plus twice S1 dot S2, and that means S1 dot S2 is S square minus S1 square minus S2 square by 2, and then to get the expectation value we have this. And remember one thing, that spin is always measured in the units of H cross. Therefore, we have one H cross from here and another H cross from here. Therefore, overall, when we will measure talk about the total spin or spin of individual particle S1 is, we should write half H cross or 1 H cross or 0 H cross. Therefore, spin is measured in the units of H cross. Therefore, overall, this will carry the dimension of H cross square. Now, if we are talking about a spin one object like a rho meson, like omega meson, like K star meson, then this expectation value will be 2 minus, we are forming from spin half object, and if we are talking about spin 0 object, this will be 0 minus half plus 1 minus half plus 1 upon 2. You see, this will turn out to be a positive quantity. This will turn out to be negative quantity. Therefore, here we are talking about this expectation value will be with a positive sign for spin 1 object, vector mesons, and for spin 0 object, this will be with a negative sign. And that is why we are finding out that because of this spin-spin interaction giving rise to a positive contribution to the meson mass, while it is giving rise to a negative contribution to the meson mass. This is what we have written it here. And then when we evaluate it for a spin 0 particle, this is turning out to be minus 3 by 4 H cross square, while for a spin 1 particle, this is turning out to be simply H cross square by 4. Therefore, this is spin 1 parity odd, simply spin 1. We are talking about the ground state, L equal to 0 state in both the cases. Therefore, in the ground state, L is 0. Therefore, the total is angular momentum is the spin of the particle. Now, we know that if mass of U quark and mass of D quark inside the meson is 308 MeV, this is not the current quark mass. This is not the quark mass in the free state. We are talking about quarks which are making up the hadrons. And if we take it to be 308 MeV, remember when we talk about protons mass is 938 MeV. There are 3 quarks, therefore 938 by 3, approximately 310. A lambda particle, 1115 MeV. U and U D quark, they are contributing 308 MeV. And then S quark, that would make 1115 MeV, has a mass of 483 square. Now what we do, we take all the 9 mesons which are member of this meson nonnet having spin 0, all 9 mesons which are member of this vector mesons, that means all 18 particles together, and do a least square fitting to get the value of this A. Therefore, 18 particles, they have been put together to get the value of the unknown constant. We found that with a value of something like twice mu by H cross whole square times 159 MeV, we get the best description of all the mesons, 18 mesons, those exist in spin 0 and spin 1 state. Remember, we had h cross square in the while we were writing the spins of the particle for the expectation values, h cross square by 4 or minus 3h cross square by 4. Therefore, h cross square is there to cancel this dimension. And then what I had told you that we have mq and mq bar. This mu square will cancel that dimension. And then I told you, because we are talking about mq plus mq bar plus something, that overall the dimension should be of the dimension of energy. Therefore, what you find out that with that value of A, we are able to calculate the masses of all the mesons, pion, kaon, eta, rho, omega, k star, phi, pseudoscalar mesons as well as the vector mesons. And as you can see by the simple analogy of adding the spin-spin interaction, which is with a positive sign for vector meson and negative sign for pseudoscalar mesons, we are able to explain the experimentally observed numbers. Therefore, we say that like we have hyperfine structure in the case of hydrogen atom, here we have the spin-spin interaction, which is giving rise to additional energy in the case of vector mesons and a reduced energy in the case of pseudoscalar mesons. Similarly, when we talk about the masses of baryons, then I told you that here in the case of baryons there will be 3 quarks, and when there will be 3 quarks, there will be spin-spin interaction between 1 and 2, 1 and 3 and 2 and 3, and therefore this S will be, this S that we spoke about, this will be S1 plus S2 plus S3, and that is why you will have expectation value of S1 dot S2, S1 dot S3 and S2 dot S3. That is what I have written here for the 3 baryons, M1 plus M2 plus M3, a proportionality constant M prime, 1 and 2, 1 and 3 and 2 and 3. Since if we talk about a delta, 4 deltas and proton, neutron, all of them are made up of U and D quarks. When we include a strange quark, then we will have additional terms. This we cannot write in this fashion, therefore then we have to evaluate individually, but that is again trivial. We will do it while doing the problem solving, and therefore the mass of the nucleon is this much. Similarly, mass of the delta will also be equal to this much, but at the same time this guy, as we have evaluated earlier, will be given by the same expression. Now you see, for nucleons, proton, neutron, or even that will be true for lambda, sigma, cascade, J is half, while J is 3 by 2 for all the baryon decuplet. Therefore, for all the non-strange mesons where you have U and D, then this J will be half for baryon octet, and this J will be 3 by 2 for baryon decuplet. What you will find again here, that this expectation value will be a positive sign for the decuplet, that means deltas, omegas, etc., and with a negative sign for the for the octet. Therefore, this is going to give you additional mass because of a spin-spin interaction, and this will give you a reduced mass because of the spin-spin interaction. This is what we can obtain for nucleon and delta. Similarly, for omega, which is made up of 3 strange quarks, we can write it here. Again, you see, to get the best value inside these particles, we are choosing these values for A prime, Mu, Md and Ms. And now with 10 decuplets members, 8 octet members, that means all those 18 particles, we can fit it by this number. And what has been found out, that the calculated value and the observed value, they are very well in agreement. And therefore, we say that quarks, not only they are required to understand the anomalous magnetic moment of the nucleons or other particles, or they are required to understand the excitations of the baryons and mesons, but with using the quark model, correctly we can obtain the observables like charge of the particles, magnetic moment of the particle, masses of the particles in the quark model. Let us stop here, and in the next class we shall talk about the kinematics of the interaction. Thank you very much.